Right now, you're drifting through a hollow in the universe, 2 billion light-years wide, confirmed in 2013, and almost no one noticed. We live in a cosmic low tide, where galaxies thin like breath on cold glass, and even time seems to stretch unevenly. By the end of this story, you'll see how that emptiness may be rewriting what we think we know about the universe. Keenan, Barger, and Cowie weren't chasing headlines. They were counting galaxies. More than 35,000 shards of time, pulled from near-infrared maps that look through dust the way X-rays look through skin. Their quiet census, by the trio whose initials would later name the KBC Void, plotted each point as a fossil of light, stretching billions of years into the past. Each point was a fossil of light, a bead on a thread running billions of years into the past. And when they laid those beads across the sky, the pattern refused to sit still. In every direction, the same bruise appeared. Too few galaxies close in, too many farther out. We weren't at the center of the web. We were sitting in one of its hollows, the empty cell that gives the lattice its shape. Cosmology had long trusted a simple compass. On big enough scales, the universe should average out. No special addresses, no favored corners, just a smooth horizon. This map suggested an exception large enough to make the compass wobble. A bubble of underdensity stretching nearly 2 billion light-years. A shallow basin in the cosmic crust. Inside a basin, gravity tugs less. Space itself relaxes a little faster. And the yardsticks we use to time the universe, its expansion rate tick high. Step outside the basin, and the tempo drops back to the wider rhythm. That split is the ember at the heart of a decade of argument. Why nearby measurements run hot, while the early universe story runs cool. In 2013, a quiet paper traced this basin. No headlines. No servers crashed. Keenan, Barger, and Cowie gave the void a coastline, and a way to see why our local numbers argue with the universe's oldest light. Picture a single soap bubble nested in a vast foam. From the inside, every point seems to drift away a touch too fast. Because the walls, those denser rims, pull matter outward. The deeper you stand in the bubble, the quicker your local metric stretches. To someone watching from beyond the wall, nothing looks unusual at all. The follow-up data were as unshowy as the claim. All sky maps in the optical and near-infrared averaged to a shortfall of roughly 20% out to about 300 megaparsecs, just enough contrast to nudge local expansion up by a few percent. It wasn't a verdict, but the arithmetic rhymed with the mystery. Skepticism is a reflex, not a flaw. How likely is it that such a hollow is ours? Within the standard cosmological model, the one with a cosmological constant and cold dark matter, the odds are long, perhaps 1 in 10,000, but rare isn't never. And a universe this broad has room for outliers and odd addresses. If that's where we live, our instruments aren't liars. Our vantage point is the variable. The insight is disarming in its simplicity. Space does not expand on a blank table. It flows over terrain. Sound travels differently in mountain air than it does at sea level. Light and motion pick up the same accent in a thinned-out cosmos. What looks like extra acceleration may be the slope beneath our feet. So the paradox may not be in the universe at all, but in the habit of flattening it in our heads. We may be standing in a valley, emptier, quieter, deceptively level, watching the horizon ease away faster than it truly does. And if that's the case, the so-called crisis dissolves into a reminder that before we rewrite physics, we should check the ground we're standing on. Early universe inferences from the cosmic background prefer about 67 kilometers. Both sides show mature pipelines, blind analyses, and rigorous uncertainty budgets. Because the expansion rate anchors the entire cosmic distance scale and timeline, shift that anchor, and ages, sizes, and cosmological parameters slide together. They framed it as a simple question and hit the nerve of modern cosmology. Two gold standard ways of timing the universe do not agree. The local distance ladder reads a faster cosmos. circling around about 73 kilometers per second per megaparsec, while the early universe route, drawn from the oldest microwave light, settles near about 67. Both camps run hardened pipelines with blind analyses and tight error bars. The mismatch is not a rounding error. It is a clean 9% gap that refuses to dissolve. If both stories are right inside their own rules, then the map we use to describe reality is missing a contour line where it matters most. This is not just a quarrel over a constant's nickname. The expansion rate is the anchor for every cosmic distance and for the timeline we teach. As if it were a finished calendar, shift the anchor and ages slide, sizes breathe, and the whole parameter sheet creaks. Push the rate higher and the inferred age of the universe comes out shorter. Pull it lower and structures must grow longer under gravity's slow hand. Dark energy's character is read off that background tempo change the baseline, and you reinterpret why supernovae dim and how the baryonic ripples in galaxy maps set their scale. Every dataset that traces growth or geometry leans on this calibration. So the disagreement is not cosmetic, it changes the story everywhere at once. The nearby measurements climb a ladder built the careful way, rung to rung, geometry to physics. Parallax lays down the first plank, with distances that do not ask you to believe any model at all. Cepheid variables take the handoff, bright and rhythmic enough to be seen across neighboring galaxies. Type 1a supernovae carry the signal to cosmological scales with calibrated light curves, while maser disks, the tip of the red giant branch, and detached eclipsing binaries check the arithmetic from odd angles. Each rung has its own ways to fail: selection effects, dust, metallicity, crowding, but independent telescopes and teams keep shaving those edges down. After years of revisions, the ladder still points to the fast number, the residuals behave, the uncertainties tightened, and the song remains the same. The far-view method begins with the faint embroidery in the microwave, afterglow. Patterns so small they read like sand ripples left by a vanished tide. Those ripples encode physics from before stars existed, fit a physical picture to that spectrum, and the parameters fall into place. Within the standard cosmological model, the preferred background tempo lands near about 67 kilometers per second, per megaparsec. No one pretends this is a direct stopwatch on today's neighborhood. It is an extrapolation from a crisp early snapshot, marched forward by a specific model. Fold in the baryon acoustic ruler, and the primordial element counts, and the constraints tighten without climbing to the local value. Consistency across independent early probes lends the result its authority. Each side is internally clean. Taken together, they will not shake hands. When two precise truths refuse to meet, the stakes shift from numbers to method and philosophy. Maybe there are systematics still hiding in the latter, subtle biases in how we calibrate cepheids in crowded fields, dust laws that drift with environment, supernova populations that change with host galaxies at low redshift. Maybe the early universe inference carries its own quiet assumptions, slight mismatches in recombination physics that tilt the acoustic ruler, foreground residues, or beam systematics that bend the fit. Or maybe both methods are pristine and our environment is not a perfect average. A large underdensity would let space stretch a little faster here without breaking any laws. And observers inside would measure a rate that looks high while observers outside would not. Each branch implies different instruments to build, different surveys to fly, different theories to cultivate. Choosing too soon risks steering decades of work toward the wrong horizon. Imagine what a genuine underdensity would do to the things we actually measure. Peculiar velocities would tend to point outward, as if the basin itself were exhaling. Measured redshifts would fold together the global expansion, and a coherent flow across hundreds of millions of light years. Distance indicators inside the basin would register a slightly inflated recession field. Farther out, as our sightlines cross the rim and sample denser terrain, the effect would taper and the numbers drift toward the global average. A gradient like that could stitch the near universe to the far one without asking nature to rewrite gravity. And if the neighborhood is ordinary after all, then the argument rolls back to fundamentals. Perhaps dark energy is not a perfectly constant pressure, but a field with a pulse, evolving just enough to move the dial without wrecking everything else. Perhaps gravity wears different shoes on gigaparsec scales than it does in the solar system, leaving growth rates gently altered while local tests stay pristine. Even new light species, or a brief early time push, have been floated, each with predictions sharp enough to be hunted down. Elegance is cheap, survival through cross-checks is expensive. This is why people outside cosmology should care about a 9% quarrel. Those numbers set the wattage of stars, the budgets of feedback, the timelines for planet formation, and the bounds particle physics places on new sectors. Gravitational wave standard sirens are coming to join the chorus, promising their own calibration of distance and time. If the baseline is off, the ripples spread. So the stakes are empirical, theoretical, and strategic at once. Empirical, because we have to map matter and motion without flattering our expectations. Theoretical, because any model we keep must cradle all the good data at the same time. Strategic, because instruments and surveys spend decades of human lives and national budgets. A wrong turn wastes both. The only adult posture now is layered redundancy and orthogonal tests. Pressure testing every rung, every extrapolation, every assumption about the ground beneath us, until the map and the terrain line up. Confidence and credibility are not moods, they are earned. In the end, either we live in an unusual patch, or physics asks for an addendum. Both outcomes are profound. The method demands patience over rhetoric, and curiosity with guardrails. Our instruments are sharp. Now our perspective has to be sharper. Before we declare new laws, we should check the slope under our feet. The story begins quietly, without fireworks or press conferences. In 2013, Ryan Keenan, Amy Barger, and Len Cowie were charting galaxies in infrared light. They used two complementary near-infrared sky surveys, the 2-micron All-Sky Survey and the United Kingdom Infrared Deep Sky Survey, to measure local density fields. Their goal was not revolution, it was calibration of the nearby universe. Infrared wavelengths see through cosmic dust, revealing structures invisible to optical surveys. By combining multiple redshift catalogs, they traced galaxies out to 400 megaparsecs. That covers almost 1.3 billion light-years, enough to test cosmic homogeneity directly. They built radial profiles, how many galaxies per unit volume as distance increases. Then they compared these profiles to predictions from the standard cosmological model. If the universe is homogeneous, the number density should flatten beyond 100 megaparsecs. Instead, it continued climbing. Fewer galaxies nearby, more at larger distances. The trend was robust across hemispheres, filters and morphological selections. Statistical noise, photometric errors, and masking were ruled out by careful control samples. The residual pattern survived every sanity check they could design. When plotted, the profile formed a shallow bowl of underdensity around our position. Its depth corresponded to roughly 20% less matter than average. Its radius, between 250 and 300 megaparsecs, was enormous by any cosmic standard. No known local void matched that scale or symmetry. Smaller voids pepper the cosmic web, but none encompass such a volume continuously. The discovery implied we inhabit the center of a massive low-density region. It became known informally as the KBC Void. Keenan and colleagues cross-checked their finding using K-band luminosity densities. The advantage: infrared luminosity traces stellar mass better than optical flux. They integrated over luminosity functions to convert brightness into mass density. Every approach returned the same answer. Local space was underdense by tens of percent. They also verified that photometric zero points and Malmquist bias could not explain it. The deficit persisted even after correcting for survey completeness and K corrections. To place their region in context, they compared to farther redshift slices using SDSS data, beyond about 400 megaparsecs. The density curve flattened as expected from homogeneity. This transition suggested a void bounded by denser walls, the cosmic equivalent of a basin. Within it, galaxies are spaced farther apart. Outside, clusters tighten again. Such geometry affects the average expansion rate measured inside versus outside. It was a potential natural explanation for why local expansion appeared faster. The team was conservative in language. They did not claim a solution to the Hubble tension, then barely forming as a debate. They reported an observed underdensity consistent with large-scale structure fluctuations. Still, their figures spoke louder than their caution. The amplitude and extent were larger than typical the standard cosmological model simulations, produced spontaneously. If real, our neighborhood was statistically unusual at the 1 in 10,000 level. Subsequent work sought confirmation through independent tracers of matter distribution. Galaxy cluster catalogs and radio surveys found similar density gradients in broad strokes. Supernova counts showed mildly enhanced rates at larger distances, matching the trend. Weak lensing maps hinted at lower projected mass densities locally. Even measurements of galaxy cluster motion in the cosmic microwave background showed coherent outflow patterns from nearby clusters. Each dataset added context. None contradicted the basic underdensity picture. To appreciate the challenge, consider how hard mapping our own region truly is. We live inside the Milky Way, immersed in its dust and gas plane. The zone of avoidance obscures about 20% of the sky from optical view. Infrared and radio wavelengths pierce that veil, but introduce their own systematics. Distance estimators rely on redshifts converted via the Hubble law we are testing. Thus, every step requires iterative self-consistency checks and model independence. Keenan's group used flow-corrected distances to minimize local velocity contamination. They compared several velocity fields and found the results stable within uncertainties. One of their key figures, a logarithmic plot of luminosity density versus distance, shows the void clearly as a dip centered on the local group. At a redshift of about 0.07, the curve rises toward the cosmic average again. That rise marks the void's edge and the return to statistical homogeneity. The total volume encompasses hundreds of millions of galaxies and billions of years. It is the largest structure ever proposed to enclose our position symmetrically. Once published, their paper triggered quiet reanalysis in observational groups worldwide. Some teams questioned the void's depth or extent, citing sample variance limitations. Others argued that infrared luminosity might miss low-mass dwarfs in the local volume. Yet, when expanded datasets arrived in 2017 and 2020, the underdensity remained. The exact numbers shifted slightly, but the qualitative pattern persisted. That persistence forced cosmologists to treat the possibility seriously. Parallel analyses looked for corresponding signatures in the velocity field. If matter is less dense, galaxies should drift outward collectively. Surveys of peculiar velocities indeed showed bulk flows pointing away from the local group. The magnitude of those flows aligned with simulations of a void of KBC size. The velocity evidence was no longer circumstantial. It was predictive and quantitative. By the early 2020s, the KBC Void had evolved from an oddity to a testable hypothesis. New surveys, such as the Dark Energy Survey and the European Space Agency's Euclid mission, plan to map the cosmic structure in 3 dimensions with high precision. Independent datasets from radio, infrared, and supernova archives provided cross-checks. The goal shifted from proving existence to measuring exact geometry and contrast. Its size, depth, and profile became inputs for re-evaluating the Hubble constant locally. At its core, the discovery was simple science executed patiently and precisely. Count the galaxies, map their light, compare to the expected average. What emerged was not a mistake but a mirror, showing how fragile our assumptions are. The KBC Void reminds us that even cosmic principles rest on observational foundations. And foundations can tilt, quietly, when we finally measure them well enough. By the mid-2000s teens, a troubling pattern stopped looking like noise. Every careful local measurement pointed to a faster expanding nearby universe. Those analyses converged near about 73 kilometers per second per megaparsec. Independent teams repeated the work and landed on essentially the same pace. Meanwhile, early universe inferences told a different, slower and stubborn story. Those preferred about 67 kilometers per second per megaparsec instead. Both sides were precise, consistent, and peer-audited across multiple instruments. The numerical gap looked small, yet its meaning was enormous. Local measurements rely on a distance ladder, built rung by rung. Parallax provides a geometric foundation, without astrophysical guesswork or templates. Cepheid variables extend that foundation cleanly across significant extragalactic distances. Type 1a, supernovae bridge to truly cosmological scales with standardized luminosities. Other cross-checks reinforce the ladder's structure from different systematic angles. Water megamasers give geometric distances from rotating nuclear disks. The tip of the red giant branch offers a complementary stellar candle. Detached eclipsing binaries supply additional anchors where conditions permit. After years of recalibration, the ladder still favors the faster number. Uncertainties shrank, while residuals remain statistically well-behaved. The global viewpoint starts with the universe's ancient afterglow. The cosmic microwave background encodes physics from the hot early epoch. Tiny patterns in temperature and polarization trace primordial acoustic waves. Fit a physical model to those patterns, and parameters fall out. Under baseline assumptions, today's expansion comes out slower and remarkably tight. Multiple experiments agree on about 67 kilometers per second per megaparsec. Add information from baryon acoustic oscillations and primordial element abundances. The combined constraints sharpen while stubbornly resisting an upward shift. These approaches measure different things in different ways. Local techniques measure today's expansion directly in the nearby universe. Early universe methods infer today's rate by evolving forward from first principles. If the underlying model changes, the derived value can slide. However, proposed extensions often fix one tension while breaking another. As precision improved, the contradiction deepened instead of dissolving. Intermediate arbiters promised to settle the matter and failed. Strong lensing time delays measure expansion without the microwave background. Those results frequently cluster near the faster local number. Conversely, combined baryon acoustic oscillations with supernova distances in nucleosynthesis tend to support the slower global number from early universe physics. Cosmic chronometer methods using differential galaxy ages lean slow as well. The middle did not converge. It split into two coherent hills. Systematic errors remain the first suspects for many careful readers. On the local side, environmental geometry might bias nearby expansion estimates. If we inhabit a large underdense region, velocities skew outward coherently. Peculiar velocity corrections could underappreciate bulk flows on 100 megaparsec scales. Calibration chains across space telescopes and parallax catalogs carry subtle risks. Metallicity dependencies in cepheids might hide several percent of drift. Individually, these issues look small. Together, they could nudge results downward. On the global side, model rigidity is the primary concern. If the early universe contained additional fast-moving energy components, the standard ruler scale would shift and lift the inferred expansion. Brief episodes of early dark energy try to raise the final number. Yet each tweak invites fine-tuning or clashes with other precise datasets. The baseline model remains economical, predictive, and hard to dislodge. Both communities harden their pipelines and publish with notable restraint. Neither camp sees messy scatter that would betray large hidden problems. Meta-analyses now reveal two peaks with very little statistical overlap. One sits around about 67 kilometers per second per megaparsec. The other sits near about 73 kilometers per second per megaparsec. Within published uncertainties, these peaks refuse to meet in the middle. The disagreement has surpassed ordinary work-in-progress territory. It is now a defining question for precision cosmology. Consider what an unusual environment would imply observationally. Inside a large underdense region, matter fails to slow expansion efficiently. Galaxies develop outward motions that align rather than cancel on average. Local distance indicators would register a slightly inflated recession field. As observers look farther out, the effect should gradually diminish. Measurements crossing the region's edge should drift toward the global number. Some recent analyses hint exactly at that distance-dependent trend. The hints are not final, yet they point in the predicted direction. If the environment does not explain the difference, theory must stretch. That would push us toward physics beyond the standard cosmological picture. Dark energy might evolve with time, rather than stay perfectly constant. Gravity could behave differently on gigaparsec scales than in the solar system. New light particles might have influenced early acoustic physics subtly. Any such idea must survive a gauntlet of independent cross-checks. So far, no candidate satisfies everything without collateral contradictions. Why does this matter beyond a single constant's value? Because the expansion rate calibrates ages, sizes, and energy budgets everywhere. Shift to baseline, and galaxy formation histories move with it. Black hole growth, feedback, and background radiation fields change accordingly. Particle physics bounds, depending on cosmological parameters, would be reinterpreted. Even future gravitational wave sirens will tie into this calibration chain. Precision elsewhere ultimately depends on truth here at the foundation. The human side of the story deserves a clear sentence. Two expert communities are both correct within their respective frameworks. Both refuse to smooth the disagreement with rhetoric or hand-waving. Conference is open, with honest disclaimers. There is no resolution today. Funding agencies now treat the issue as a strategic priority. Young researchers build careers designed to pressure test every assumption. The result is an unusually productive disagreement that sharpens the field. For now, the evidence reads like two simultaneous truths. Local measurements describe our immediate cosmic neighborhood with exquisite detail. Early universe inferences describe the grand stage with equally impressive power. If we truly sit inside a large underdense region, both can be right. One reports the nearby terrain, the other reports the global map. Bridging them requires tests that track how measurements change with distance. Those tests are underway and already shaping survey strategies. Summarize the contradiction in the simplest possible language. Local techniques favor about 73 kilometers per second per megaparsecs. Early universe routes favor about 67 kilometers per second per megaparsecs. Uncertainties are small, overlap is negligible, confidence is high on both. The options are hidden systematics, unusual environment, or genuinely new physics. The next block examines the environment path directly, the void hypothesis. What if both numbers are right because the universe is not uniform where we stand? That question pushed several astronomers toward a simple answer. Geometry. Our region may sit inside a vast, underdense volume called the KBC Void. Inside it, space expands slightly faster because there is less matter to slow it down. Outside it, gravity from denser filaments pulls more strongly, restoring the global average. A difference of only 10 or 20% in matter density could inflate the local expansion by the observed amount. Imagine standing in a shallow valley surrounded by distant mountains. Gravity pulls you toward the slopes, which means away from the valley's center. In cosmic terms, galaxies inside a void feel that same outward pull. All the mass lies beyond the edges, so every object inside accelerates outward. From within, the whole sky appears to drift away a little faster than theory predicts. From the outside, the same space would look slightly slower. Perfectly ordinary, perspective becomes physics. The KBC void is not a tiny cavity or a small cluster gap. Its estimated radius is nearly 1 billion light-years, 2 billion across end to end. Within that volume, average density falls roughly 20% below the cosmic mean. The shape is nearly spherical when averaged over many surveys. Infrared galaxy counts, radio catalogs, and supernova distributions trace its contour. At its outer boundary, the density rises again toward the familiar cosmic web. This boundary lies close to the transition zone. Here, the expansion we measure steps down from about 73 to about 67 kilometers per second per megaparsec. That coincidence turned the KBC void from curiosity into candidate explanation. How would such a void form in the first place? Gravity builds structure by pulling matter into clumps, leaving empty spaces between them. Simulations of large-scale structure naturally produce a network of filaments and bubbles. Most voids, however, are smaller, tens or hundreds of millions of light-years across. A region as large as the KBC void is rare but not impossible within statistical extremes. Given the universe's vast size, at least a few supervoids that deep should exist somewhere. It just happens that one of them appears centered on us, or near enough that we live inside its walls. Inside this geometry, the laws of physics remain intact. Only the environment changes. Galaxies here participate in two motions simultaneously: the global cosmic expansion and an additional coherent outflow away from the void center. That outflow adds extra velocity on top of the standard Hubble flow. When observers inside measure redshifts, they record the sum of both components. Hence, local determinations yield a slightly inflated expansion rate. Observers farther away beyond the void see no such bias. Numerical models have tested this scenario with increasing realism. Simulations of voids having a 20% density deficit reproduce the needed offset between local and cosmic expansion, roughly 9%, the very size of the tension. They also generate bulk flow velocities matching observed galaxy motions of several hundred kilometers per second, directed outward from the local region. Maps of peculiar velocities, galaxy surveys, and supernova statistics all show hints of this coherent outward pattern. Even the cosmic microwave background exhibits subtle anisotropies aligned with it. Each signal alone is modest. Together they sketch a consistent landscape. The void hypothesis also explains a long-known observational puzzle. Measurements of the expansion rate decline gently with distance. Nearby galaxies yield the highest values, around about 73 kilometers per second per megaparsec. As samples extend beyond roughly 2 billion light-years, the value approaches about 67 and stabilizes. That transition radius coincides with the estimated edge of the KBC void. In other words, the universe appears to expand fastest exactly where it is emptiest. It is a simple pattern with elegant consequences. For visualization, picture a cosmic bubble roughly centered on our position. Inside the bubble, space stretches a bit faster. Beyond the bubble, it slows to the global rhythm. Astronomers sometimes call this idea the Hubble bubble. The analogy fits: a localized region whose internal pressure makes it expand faster than its surroundings. The physics is gravitational, not gaseous, but the metaphor captures the effect intuitively. Light leaving distant galaxies passes through this bubble on its way to our telescopes. Because gravity inside is weaker, photons lose slightly less energy to cosmic work. That subtle difference alters redshifts and distances in measurable ways. Skeptics point out that living inside such a void feels statistically unlikely. Standard cosmology predicts that regions this large and this deep should be rare. Finding ourselves within one seems like improbable timing, just when our instruments become precise enough to notice. Yet rare is not impossible. Someone has to occupy the tail of every probability curve, and the evidence keeps accumulating. Infrared surveys, radio maps, peculiar velocities, each reinforcing the notion that our neighborhood is not perfectly average. If the KBC void truly influences local measurements, it reframes the Hubble tension entirely. Local methods would remain accurate for this location only. Global methods would describe the universe as a whole, beyond our valley. Both truths coexist once we accept spatial variation as part of the picture. Instead of demanding new particles or exotic gravity, we acknowledge that our cosmic address introduces a measurable bias. Testing this hypothesis is straightforward in principle. but demanding in practice. We must map galaxy density and motion far beyond the void's boundary. Future surveys, such as Euclid, the Vera Rubin Observatory, and the James Webb Space Telescope, can extend standard candles and standard rulers deep into the surrounding filaments. If the void model is correct, expansion rates should decrease smoothly with distance. The flow of galaxies should reverse direction at the edge, as gravity reasserts itself. Temperature patterns in the microwave background should align with the void's profile. Each of these signatures is observable. None require new physics. The void hypothesis does not dismiss dark energy or relativity. It merely reminds us that geometry matters, even at the largest scales. Our measurements are not taken from nowhere. They are taken from here. When cosmologists speak of the universe's acceleration, they must now ask, acceleration relative to what region? Inside the void, faster expansion is a local truth. Beyond it, the universe follows its slower, global rhythm. If this picture holds, the so-called crisis dissolves gracefully. The two expansion rates are not contradictions, but coordinates. We live in a valley of density that stretches the fabric of space a little thinner. From our vantage point, the cosmos races away at about 73 kilometers per second per megaparsec. From the outside, it flows at about 67. The average heartbeat of creation, perspective, not physics, created the tension. Understanding that may be the most human discovery of all. Even in the vast universe, where we stand still matters. They did not stop at sketches. They grew universes inside machines. Start simple, tiny fluctuations. Gravity, dark matter, dark energy. Let it run, and structure blooms. Filaments thread the dark, clusters knot at crossings. Cavities open like breath held too long. A void is just a place, slightly poorer in matter than average. The question is not whether voids exist. They do. The question is whether one broad and deep enough could match the KBC outline we see from here. In the standard cosmological model, simulators move billions of tracers through an expanding grid. The universe begins smooth. Contrast rises as gravity amplifies whispers. By today, the box looks like a web of light and shadow. Typical voids span tens of millions of light years. Supervoids sometimes reach a few hundred million, a cavity almost 2 billion light years across, down by roughly 20% is rare. Think 1 in 10,000 rare, improbable, not forbidden. In a cosmos this large, the tail of the curve still happens somewhere. Teams then insert a KBC-like underdensity and watch the clock. Inside the hollow, the measured expansion tilts high, about 73 kilometers per second per megaparsec. Outside, it relaxes toward about 67, the global rhythm. Light crossing the basin picks up tiny gravitational shifts, enough to recreate the gentle slope we see in real Hubble plots. Velocities fall into place without being forced. Galaxies drift outward from the basin's center at a few hundred kilometers per second, matching bulk flow catalogs. Geometry alone can mimic a faster universe. No extra forces, no exotic fluids, but the trick is fragile. Shave the depth or the size, and the split nearly vanishes. The model wants broad, deep, and roughly centered. Push it off to one side, and you get anisotropies we do not observe. Modelers like the fit and worry about the odds. A fluctuation that large, inside vanilla assumptions, sits far out on the tail. It is a mountain taller than Everest, on an otherwise flat plane. Possible, cosmologically rare. Some say that level of coincidence feels as strained as tweaking dark energy. If everything is unlikely, which discomfort do we choose? Others point to the sky itself. Infrared maps, radio counts, supernova fields. Their contours line up with the simulated geometry more than chance would allow. The map keeps echoing the same hollow. The storyline matured between 2015 and 2023. First came sanity checks. Could masks and selection carve fake holes? Mock catalogs produced shallow dips, not the full amplitude. Bigger datasets arrived, and the low-density region did not wash out. Groups began planting KBC scale voids into standard boxes to score probabilities and consequences. Early comparisons said tail event, but the signature matches the Hubble tension size. Then came relativistic ray tracing. Light was marched through a KBC-like landscape. Redshift, distance curves tilted by nearly the observed amount when the observer sat near the center. Off-center tests in 2022 showed small microwave anisotropies, still within current limits. By 2023, arguments shifted from yes or no to how unlikely. Exactly. Meta-analyses quoted a few percent to far less, depending on priors. Low, not negligible. Some explored gentler ways to make big hollows less rare. Raise the initial fluctuation normalization slightly, and large voids appear a bit more often, without wrecking other fits. Try non-Gaussian seeds, primordial patterns that favor emptier patches. Test models where cosmic acceleration couples weakly to matter. Each tweak buys plausibility at the price of simplicity. None is required if we accept an unusual address, but each remains on the table. Meanwhile, constrained simulations attempt a faithful portrait of our neighborhood. They feed real galaxy catalogs into the initial conditions and rewind the clock. Evolve forward, and an underdensity near our position reappears naturally. It is smaller than the canonical KBC depth, yet big enough to bias the local expansion by several percent, halfway to the observed gap. That hints at a mixed answer. A moderate hollow, plus modest systematics could add up to the full effect. By the early 2020s, reviews sounded cautious and adult. The void is a plausible contributor, not a magic wand. It needs no new physics and grows from the same rules that make filaments and clusters. Its statistical unlikelihood keeps skeptics on the field. Calibration could still matter. Early time modeling could still bend. Workshops now talk about multi-cause degeneracy, a blend of environment and small biases on both sides of the ledger. The deciding data are already lining up. New surveys will map density and motion across billions of light years, with uniform depth. If local and global expansion converge smoothly with distance, the void's role shrinks. If a distance-dependent drift persists along the predicted profile, the KBC picture moves from possibility to explanation. Either way, the measurement will be clean. What carries more weight? Evidence or comfort? Theory has given the hollow academic standing. It survived replication and parameter abuse across independent codes. It sits happily inside general relativity and the cosmological principle, while asking us to accept that our address is not perfectly average. Odds may be small, but evidence does not care about our taste. If the pattern holds, a quiet line joins the textbooks. The universe expands faster here, not everywhere, and the simulators warned us that rare valleys must exist. A theory survives by what the sky confirms, not by elegance. If a vast, underdense region wraps around us, it must leave fingerprints. Light, motion, temperature, each should echo the same hidden shape. Treat every dataset as a mirror, angled differently, catching the same outline. Start with the universe's ruler. Baryon acoustic oscillations. Sound waves in the early plasma froze into today's galaxy spacing. Measure that scale nearby and far, and you read how fast space is stretched. Close in. The ruler looks a touch longer, a hint of faster local expansion. Farther out, beyond the putative boundary, the scale drifts back to normal, a smooth return, the kind geometry would predict if a hollow sits around us. Gravity also brushes the background light. As the cosmic microwave afterglow crosses changing terrain, photons gain or lose a whisper of energy, stack many large voids, and the temperature nudges upward by microkelvins, a faint rise that has been seen. The famous cold regions on the sky complicate the picture, yet their scale and orientation sit near what a KBC-shaped basin would imprint, not a shout, a smudge in the right direction. Motion tells the same story. Peculiar velocities ride on a global flow like leaves on a river. Map distances for thousands of galaxies, and a pattern emerges, several hundred kilometers per second, streaming away from the underdense zone, curving toward the heavy walls around it. That is what a basin does when it breathes. It drains toward its ridges. The measurements are noisy, yes, but the alignment holds across independent compilations. Even the biggest dip on the microwave sky, the cosmic dipole, can carry a local accent. Part of it is our orbital motion. Part may be the net drift of our broader neighborhood. If a hollow adds outward flow, the dipole nudges high by a small margin. Satellites see a hint of that excess within systematics, but pointed the right way. Elsewhere, several cooler patches coincide with known underdensities traced by galaxies. No single patch proves a void. Taken together, they hum in the same key. Scale up to our address in Laniakea, a gravitational domain about 500 million light-years wide. Rivers of galaxies fall toward the great attractor beyond our dust lane. Reconstructions of three-dimensional flows give the local group a speed near 600 kilometers per second. The vector makes sense if two hands push and pull, attraction from the massive ahead, and a gentle outward shove from the basin we occupy. Push and pull, the Milky Way moves as the balance demands. Standard candles weigh in too. Type 1a supernovas trace a smooth brightness, redshift curve in a uniform cosmos. Nearby, they sit slightly brighter than the global fit, as if closer than expected. That offset corresponds to an expansion near about 73 kilometers per second per megaparsec. Beyond roughly 2 billion light-years, the slope relaxes toward about 67. Surface brightness fluctuations and Tully-Fisher distances lean the same way. Different tools, same tilt. What strengthens the case is not one spectacular signal, but many quiet agreements. Density fields, velocity maps, temperature patterns, each responds to gravity differently. Yet their scales and axes line up when processed through the same geometric lens. Where galaxy counts dip, velocities radiate outward. Where the flow changes sign, supernova slopes flatten. Even the background and anisotropies trace a similar diagonal across our local sky. Shared systematics can fake echoes, footprints, 0 points, sky coverage, but as precision climbs, coincidence loses stamina. The deciding maps are inbound. The Rubin Observatory will net millions of supernovas, a yardstick across vast ranges. Euclid and the Nancy Grace Roman mission will chart weak lensing directly. Mass, not light. If they see a deficit aligned with our region, the picture hardens. If uniformity returns once calibration matures, the hollow retreats to an elegant detour. Either way, the test is clean. For now, the balance tilts but does not topple. Independent checks keep sketching the same silhouette. A faster expansion here, not everywhere. Whether this basin alone can close the full 9% gap is the last question. The answer decides how we talk about the universe and how much our location edits the truth we measure. By now, the argument has lapped the whole sky. We counted galaxies, mapped flows, built voids inside machines, and checked the hardware twice. Every path loops back to the same split, two expansion rates that both look right. The fast number, about 73 kilometers per second per megaparsec, comes from the nearby universe, read by geometry. The slow number, about 67, emerges from the oldest light. Between them is not confusion, but an unfinished shape in reality. Some pieces are solid. Our neighborhood is underdense compared with the global mean across infrared, optical, and radio counts. That geometry leaves marks, bulk flows of a few hundred kilometers per second, drifting outward, and a gentle slide in the apparent expansion with distance. The tension itself is real. Different instruments, different bands, different epochs keep returning the same pair of values. Statistics cannot wish a gap this clean out of existence. Simulations agree that a basin down by roughly 20% can reproduce the offset rare, allowed by the same gravity that we trust everywhere else. Other pieces are still contested. A hollow nearly 2 billion light-years across sits on the thin tail of expected fluctuations. Skeptics call it a coincidence that merely moves the mystery. Others point to quieter biases that may still hide in the margins. Metallicity in Cepheids, parallax 0 points, color laws in Type 1a light curves. Even the global side lives inside a model of the early plasma, and that model evolves when new data arrive. Each pass tightens the room for error. None closes it completely. What this is not is a broken instrument. A decade ago, the usual suspects were calibration, dust, mislabeled data. Those trials have been run to exhaustion. Ground and space agree inside their lanes. Optical and infrared agree. Near and far agree. No single telescope or pipeline holds the steering wheel. The contradiction survives every upgrade, which is what inconsistencies do when they belong to nature, not to hardware. What we still need are maps that bridge the rim and keep going. Distance indicators that work from the local group to billions of light years with the same calibration end to end. The Rubin Observatory will stack millions of supernovas. The European Space Agency's Euclid mission and NASA's Nancy Grace Roman Space Telescope will chart weak lensing directly. Mass, not just light. The Square Kilometer Array will push peculiar velocity catalogs deeper in radio. Together they can say whether the underdensity continues, ends, or flips. The test is clear. The decision will be clean. Cosmology has stood at crossroads like this before. The surprise in supernova dimming became dark energy. A pillar, not a patch. This debate carries the same voltage. Either we live in an uncommon valley inside an ordinary cosmos, or the physics behind acceleration needs an addendum. Both outcomes refine the map, neither tears it up. The honest posture today is cautious optimism. Evidence for a local hollow is strong. Evidence that it is sufficient is not complete. The tension is real. Its meaning is open. The datasets keep pointing to a universe more structured and more subtle than the smoothed average in our equations. The next decade will tell whether geometry alone stitches the two truths, or whether something deeper in matter, in energy, or in time waits just beyond the rim. Until that verdict, the field holds its rarest healthy state, not certainty, curiosity, perfectly preserved. 90% of the universe is emptiness. Not matter, not light. That emptiness is not absence. It is the stage. Galaxies thread the dark like frost on a silent window. Clusters nod at crossings. Filaments stretch between distant gravitational shores. The picture looks fragile. The pattern holds across impossible scales. From our small address, we read meaning in the arrangement of nothing. We have chased a difference in pace. Near us, the cosmos hurries. Farther out, it relaxes. Numbers became maps. Maps became motion. Motion pointed back to place. Again and again, a faint fingerprint pressed into the evidence. Not a command, a suggestion. Geometry whispering the same sentence. Where we stand still matters. Emptiness shapes what we call normal. In a shallow valley, horizons move differently. Distances lean. Clocks drift a little. Light pays a smaller toll. The rules do not break. They follow the terrain. We inherit a local rhythm and mistake it for the global song. Then we learn to hear both melodies at once, without conflict. There is humility in that shift. Our instruments sharpened, but the answer was perspective, not machinery. The sky did not change. The map in our heads did. Cosmology grew quieter and more honest. Precision did not crown a winner. It carved a better question. What else is shaped by where we stand? 90% emptiness still leaves consequences. Voids guide flows. Flows gather matter. Matter lights the darkness. Gravity sketches borders we cannot see and never escape. We are creatures of contour, telling stories along curvature and depth. Every measurement is a conversation with shape. Every conclusion carries the accent of its neighborhood. So let the ending keep a gentle promise. If our local valley explains the split, both truths can live. Nearby, the expansion runs about 73. Beyond, it settles near about 67. Neither number is wrong. Each belongs to its landscape, and if the hollow is not enough, the search widens with grace. Either way, the cosmos asks us to listen better. Fade to quiet that is not empty. Hold a star-poor field, heavy with unseen structure. A pale halo drifts through, then slips into unlit space. Somewhere beyond the frame, filaments pull on each other softly. Somewhere within the frame, we learn to be local without being small. In the largest story, emptiness is not silence, it is time kept.